Advanced Pre-Calculus, Chapter 8, Section 3. We're going to look at dot products and vector projection. So just by way of review, Section 1, we did geometry, and it was painful and it was hard, and it was the law of sines and cosines. And then in Section 2, we started breaking down the vectors into x and y components, writing them in much easier formats, breaking them down, and finding that it was easier to deal with vectors when you can break them down into x and y into the component form. And what we're going to do in this section is realize that God did not create a flat world, and occasionally you have to break vectors down into two components that are not x and y, yet they're still perpendicular to each other. So that's what this section's all about. You did everything in the last section, breaking things down into x and y, and we're going to build on that in this section because you're going to break vectors down into components. You're just not going to break them down into x and y. You're going to break them down into other components. So just a little bit of vocabulary. A dot product, which is a mathematical construct that is useful when dealing with vectors. Orthogonal, which is a cool word, and that just means perpendicular. So if two vectors are orthogonal, they intersect at 90 degrees. A vector projection is simply a vector projected onto another vector. And we'll talk about that. And then work, which is nothing more than force times distance. Okay, so dot product, as it is explained here on this slide, a dot product, you take the first term or the x term of two vectors in component form, multiply them together. Then you take the second term or the y terms, multiply them together, and then you add those two terms together. So a dot product is a scalar. It's a number. It is no longer a vector. And the two vectors are orthogonal only if a dot b is 0. So when you calculate the dot product, if it's 0, the vectors are orthogonal. So let's look at an example here. You have two vectors, u and v. Vector u is negative 3, 4. Vector v is 3, 6. To find the dot product, negative 3 times 3, negative 3 times 3, 4 times 6. Add that all together. And you see you get 15. Since 15 is not 0, those vectors are not orthogonal. Now let's do another one. 2, 17, negative 14, 4. 2 times negative 14 is negative 28. 7 times 4 is 28, so u dot v is 0. Therefore, they are orthogonal, which means they meet at 90 degrees. That's a very useful thing to be able to do, is take vectors and know that they meet at 90 degrees, because it allows us to do triangle trigonometry without using the law of sines or the law of cosines. Okay, now I'm going to let you do this. Give you the answer in 3, 2, 1. Okay, it's negative 7. 4 times negative 3 is negative 12. Negative 1 times negative 5 is 5. Negative 12 plus 5 is negative 7. Okay, properties of a dot product. This may make sense without even talking about it, but we're going to talk about it. Order doesn't matter. A commutative property, u dot v is v dot u, and that's because you're taking the x terms, multiplying them together, y terms, multiplying them together, and adding them. Also, distributive property, if you have u dot v plus w, you can add these two together and do a dot product. You can do a dot product with v and a dot product with w, and then add them together. And scalar, you can multiply k times u, or you can multiply k times v, or you can find the dot product and then multiply k by the dot product. Zero vector dot product, anything times 0 is 0. And the magnitude of a vector is u dot u is the magnitude squared. That's going to come in really handy. And we got the proof down here. If you have the vector u written as u1, u2, the dot product u1 times u1, u2 times u2, u1 squared, u2 squared. The magnitude of u is u1 squared plus u2 squared, square root of that whole thing. So if you square the square root, you get the dot product. So the dot product is the magnitude squared, and you will see that that comes in very, very handy. Okay, use the dot product to find the magnitude. When you have a vector written in component form and you're using the dot product to find the magnitude, it really just adds an extra step, because the dot product, negative 6, 5 dot negative 6, 5 is negative 6 times negative 6, or negative 6 squared. 5 times 5 is 5 squared. It's a square root. Well, by my way of thinking, if you have this vector written in component form, you should be able to go right here and skip the whole dot product thing. The reason that this is in this section is to get you used to calculating the dot product. So you need to be aware that you can do this, and it'll come in handy later on in this section. Okay, I'm going to let you have a shot on this one. I'll give you the answer in 3, 2, 1. So using the dot product, it would be negative 4 times negative 4 plus negative 1 times negative 1. Take the square root of that whole thing, which is square root of 17. Okay. Law of cosines is used in a proof here, but what you need to know is the equation. The angle between two vectors. Cosine of that angle is a dot b divided by the magnitude of a times the magnitude of b. And we have the proof down here. Magnitude a plus magnitude b minus 2ab is equal to cosine, or times cosine theta is equal to, and the third side is c, but that's actually b minus a squared. Go through the steps to simplify and you end up with the equation. I don't want to spend a lot of time on this proof. This proof is in your book, and when you get into calculus, you will be expected to be able to do proofs like this, and in some sections, every problem will be similar to this, where you will have to prove things. Okay, so finding the angle between these two vectors u and v. U dot v over magnitude of u, magnitude of v. I recommend you write this down, and then you fill in your vectors, and then you do the dot product. Negative 3 times 2, negative 6. Negative 5 times negative 3, 15. Magnitude of this vector, it's the square root of negative 3 squared plus negative 5 squared, 34. 2 squared plus negative 3 squared, 13. And I recommend you show your work and you do each of these steps. If you skip this step and go right down to here, guaranteed you'll have a great opportunity to make a mistake. Negative 6 plus 15 is 9. Square root of 34 times the square root of 13 is just the square root of 34 times 13, 442. Now, is there a need to rationalize the denominator at this point? No, because you are trying to find the angle theta. So what you need to do is do the inverse cosine of 9 over square root of 442. If you rationalized it, it'd be 9 times the square root of 442 over 442, and you'd have to enter that into your calculator to get the angle. It's just easier to wait until your final answer to rationalize the denominator. So as a general rule, you do not need to rationalize in an intermediate step, only when you get to the answer. Okay, so that angle, when you do the inverse cosine, is 64.7 degrees. Now find the angle between these two to the nearest tenth. And when I get to the end of this one, I'm going to point out something interesting that you may not have thought of. Again, write out the equation, fill in your vectors, do the dot products, do the magnitudes, and then simplify. 2 plus negative 24 is actually negative 22. So see if you can get from here to here by simplifying. And if you can't, go ahead and ask your teacher how to do that, but it is critically important that you, A, recognize it can be simplified, and B, simplify it as much as possible. And again, no need to rationalize the denominator because you're going to do an inverse cosine. Now, if you look, this angle, pretty big, 147. When you do an inverse cosine, your answer, the output from the calculator, will be between 0 and 180. And because it is the angle between two vectors, you never have to worry about moving this to another quadrant or something like that unless it's looking for an angle bigger than 180. But when they talk about the angle between vectors, it will always be between 0 and 180. And the inverse cosine will always give you an answer between 0 and 180. So you won't need to worry about transposing that like you have in the past when you do tangent, but you're in the second quadrant or something like that. Okay, so give this one a shot. I'll give you the answer in 3, 2, 1. And if you didn't get this answer, go back and review your work. I'm not going to show the work to go through this problem. Now, the next thing we're going to look at is the projection of one vector, we're going to call it u, onto another vector called v. So over here you have vector u. What does that look like when you project it onto v? When you break u down, you'll have a vector called w1, which is the projection of u on v, and w2. So really, what you've done with this picture here of vector u is by projecting it onto v, this would be similar to breaking it down into x and y components, but rather than x, it is some vector v, which probably is not going to be the x-axis. So this projection will have some magnitude and it will have some direction, and w2 is perpendicular to that. So the cross product of w1 and w2, I'm sorry, the dot product, we haven't gotten to cross products yet, the dot product will be 0 of these two vectors. And so if you want to think about it, the projection of u on v is kind of like the shadow that you would make onto v. And I do have a couple of examples coming up that are real-world examples of how you would do this and why you would do it. And down here, oh, I accidentally hit that. Down here we have the proof going on. And again, if you have a question about how this proof works, look at it. And if you're going to take calculus, you'll need to be able to look, study, understand, and be able to use something like this proof. You may actually get into a class where you're not allowed to use this equation unless you can do this proof to use the equation. So I'm not going to spend time going through that. If you have questions, feel free to contact me and I can go through this proof with you. It's actually being able to do that's kind of a critical part of calculus. Not that proof in particular, but the ability to go through proofs and understand them. So let's find the projection of u onto v, and I've got it drawn up here. This is u, this is v. The projection is called w1, and then w2 is just the orthogonal second component. So finding the projection, again, the first thing, write the equation down. And I don't know if your teacher will give you this equation or not. If she gives it to you, you do not have to memorize it. If she doesn't give it to you, you have to memorize it. And the way that you would read this is the projection of u on v is u dot v over the magnitude of v squared times the vector v. So again, write the equation, fill in the vectors. Now find that dot product. -1 times 4 is -4. 5 times 6 is 30. And here's what's cool. Because it's the magnitude squared, the magnitude is the square root of 4 squared plus 6 squared. Because you're squaring the magnitude, it's just 4 squared plus 6 squared. 4 squared is 16, 6 squared is 36, 16 plus 36 is 52. -4 plus 30 divided by 52 times, and that would be a scalar, times your vector 4, 6. -4 plus 30 is 26. 26 divided by 52 is 1/2. So 1/2 of 4, 6 is going to give you the vector 2, 3. Now 2, 3 is the projection of u on to v. That's what you found. So remember, your original vector u is w1 plus w2. Those are the two orthogonal components. So if you have to find the second component w2, just subtract w1 from each side. w2 is equal to u minus w1. And w1 is the projection of u onto v. So u was negative 1, 5. And w1, or the projection of u onto v, is vector 2, 3. Negative 1, 5 minus 2, 3 is negative 1 minus 2 is negative 3. 5 minus 3 is 2. So w2 is negative 3, 2. So when you get down to it, the projection of u onto v is 2, 3. And then if you have to write u as a component of its projection and w2, u is 2, negative 3. Actually, it should be 2, 3. I'm going to go back a slide. I'm going to go back a slide. Yes, it should be 2, 3, not 2, negative 3. So this should be 2, 3. 2, 3. Let me scratch that out. I apologize for not catching that earlier. That's not there. That's not there. So it's 2, 3 plus negative 3, 2. And when you come over here and look at it, 2, 3, negative 3, 2 would be the vectors. So you've got it right here. So there's a lot of math involved, and I didn't explain to you why we did any of this. And we've got, after we do a couple more multiple choice on this, we'll get to some story problems that will explain where you would actually use this. Okay, I'm going to give you some time to do this. Go ahead and pause the video. And I'll show you the answer in 3, 2, 1. And there's a lot of math that goes into this because it's u dot v over magnitude of v squared times the vector v. But that is the answer that you will get. If you don't get that, go ahead and talk to your teacher. Okay, in some cases, when you do a projection, if you have an obtuse angle, your projection will actually go the other direction. Guess what? Process is still exactly the same. See what you're doing there? And I'm just going to step through. You write the equation, you fill in your vectors, you solve, and then you get the projection of u onto v, and then you find w2 the same way. I'm stepping through this pretty fast. And you find w2 the same way, and then you just add them together. So it doesn't matter if you have an obtuse or an acute angle, you end up with the same thing. And here's an example that I want you to work through to try and do that. So go ahead and pause the video. And I'll give you the answer in 3, 2, 1. Okay, that should be what you got. Now let's go to an example. And we're going to step through this example. 10,000-pound boulder sitting on a mountain, an incline of 60 degrees. What force is required to keep the boulder from rolling down the mountain? So the force vector, x is 0, y is negative 10,000 pounds. And let's get to the next page. So we have a drawing. This is your force vector. And you need to project that onto the side of the mountain. And here is something really cool because you don't really have a vector over here. You just know that it needs to be on the side, so you have to create a vector. Well, if you have to create a vector, let's make a unit vector with a magnitude of 1, and let's see how much that simplifies the process. So the vector going up the hill, the x component will be magnitude of the vector cosine theta, y will be magnitude of the vector sine theta. So if we're going to write this in component form, if we make the magnitude 1, this vector is just cosine theta, sine theta. So we're making the magnitude 1, cosine theta, sine theta, and it's written as 1/2 and square root of 3 over 2 because that's what sine and cosine theta are. So here's what happens. What is the magnitude of vector v? It's 1. What's 1 squared? 1 squared is 1. So you can just drop this whole part from the equation, and it becomes your force vector times that unit vector, or I'm sorry, dot that unit vector, and then you multiply that scalar times the unit vector. So 0 times 1/2 is going to be 0. Negative 10,000 times square root of 3 over 2 is negative 5,000 square root of 3, or negative 8,660.3 times that unit vector. Well, guess what? If you go back, let's go back. What we were looking for is if we get the magnitude of this vector, the magnitude of W1 on this vector, you need to counteract that with an equal amount of force to keep it on the hill. And because this vector has a magnitude of 1, let's click back through this. Because that vector has a magnitude of 1, if you look at the scalar that you're multiplying this vector by, this scalar is the magnitude of the new vector. So you don't even have to multiply it out to find the actual W1. You can just say W1 is 8660.3 V, and that magnitude is how many pounds of force you need to keep that boulder up on the hill. And because this is negative, because it's going down the hill, so in order to keep it on the hill, you have to do an equal and opposite vector. So same magnitude, just flip the sign. Okay, let's now look at another example. So you have a truck sitting on a hill, weighs 5,000 pounds. How much friction do you have to keep from rolling down the hill? So here's our truck, and first thing we're going to do is we're going to write the force vector is 0, negative 5,000. And the unit vector that we're going to project it on, I'm just going to make a magnitude of 1, so it's going to be cosine 15, sine 15. Now, on your unit circle, when you memorized values, you memorized 30-degree increments and 45-degree increments, not 15-degree increments. And I know you did the double angle stuff and so forth, but rather than doing all of that, rather than punching this into my calculator and writing down 4 digits, I'm going to leave this in terms of sine and cosine until we get to the final answer to plug it into the calculator. So the projection of F onto V is going to be F dot V times vector V. And great news, all we really care about is F dot V, because vector V, we made that a unit vector, magnitude 1. And since all we care about is the force, not the direction of the force, this F dot V is going to represent the magnitude of our solution. So let's go ahead and start negative, or 0, negative 5,000 dot cosine 15 degrees, sine 15 degrees. Well, 0 times cosine is going to give you 0, so you have negative 5,000 sine 15 degrees, and that magnitude, you're going to multiply that by vector V, but this magnitude is going to give you the projection, the magnitude of that projection. So your answer is just going to be the negative of this. So negative 5,000 times sine 15 is negative 12 1294.1, and that would be in pounds. So since that's the magnitude, the force required is going to be the negative of that, or our answer is going to be 1294.1 pounds. Here we are back on our multiple choice. 1294.1 pounds is an answer, and we're off to the races. Okay, now the last part of this section is kind of straightforward, and it is talking about work, and work is force times distance. So in this mower, you are pushing with 40 newtons of force at 45 degrees, and how much work if you go 12 meters? Well, the only part of this effort that is actually work is the projection of this 40 newtons onto the flat surface. So it's just that portion of the force. And because this is the ground and it's level, that is 40 newtons times cosine of 45 degrees would be the amount of force going in the x direction. Interestingly enough, because it's 45 degrees, it would be the same amount of force going down in the y direction. So you take a look at the magnitude of the force times cosine theta is going to give you the magnitude in that direction. You're going to multiply that by 12. So it's really 40 cosine 45 times 12 is how you get to the answer on this one. And these force problems, again, it is a force over a distance. So when you're looking at the force, you just need the magnitude of whatever vector you're looking at. So in the two previous problems, we had to find the magnitude of a force on a hill. And then in this case, when you find the magnitude of a force on a hill or on flat ground like this, you just multiply it by the distance to get the work. So all we've done here is once you get the magnitude of your force vector projected onto whatever surface you're moving, then you multiply that by the distance you've moved to get the work. And this is another method which I'm not going to go over. I should have actually deleted that slide. Okay, so here we go. A person, we'll call him Bob, is pushing a crate along the floor, constant force of 30 newtons at a constant angle of 30 degrees. Find the work done in joules, and joules is Newton meters. So you have to break that force of 30 newtons down. You need the x component, which would be 30 times cosine 30 degrees. Multiply that by the distance. And you get 207.8 joules. If you got 120 joules, that would be you used sine 30 degrees rather than cosine 30 degrees. Okay, that wraps up this section. What we are going to move into in sections 4 and 5, we're going to be doing three-dimensional vectors, which is kind of intimidating to some people, but in reality, to do 3 dimensions, everything that you do in 2 dimensions for x and y, you just do it one more time for the other dimension, and that is pretty straightforward. So we'll see you on the other side.